So, first of all, a warning, you might be a Bayesian. Do you find yourself wanting to talk about the probability of effect sizes? Does the definition of a frequentist p-value or confidence interval make your head spin? Do you think that the effect sizes in ecology are equally likely to be 1 million as approximately 0? Does the following flowchart make your head spin? Do you want a single coherent way of thinking about statistical models? If any of that's true, a warning that you might be a Bayesian. So Bayesian, as defined in this book that I'll probably mention several times, Bayesian Data Analysis by Andrew Gellman and several other co-authors. There's been several editions. And they define Bayesian as using inference from the posterior distribution of parameters given data. And posterior is just a fancy word here for parameter probability distributions that come out of Bayesian models. So first, a quick aside on conditional probability, because this really features throughout everything we're going to talk about. So if I were to tell you, and this basically at the top says, what's the probability of there being something cute, given that I tell you there's a kitten? So given that I tell you there's a kitten behind the curtain, what's the probability that it is something cute? Well, it's probably pretty high, right? But what if I tell you instead that there's something cute behind the curtain? What's the probability that it's a kitten? Well, it could be something else, right? Or it could be a minion, it could be a puppy, or it could be a kitten. So what we have shown here is that the probability of there being a kitten, given that there's something cute behind the curtain, is not equal to the probability that there's something cute, given that there's a kitten behind the curtain. So this is conditional probability. We read that as the probability of something given or conditional on something else. So conditional probability matters. And this, that we will come back to several times throughout this course, is the proportional version of Bayes' rule, which is all about conditional probability. And Bayes' rule here, in this context, would say that the probability of there being a kitten given there's something cute is proportional to the probability of it being cute given there's a kitten times the probability of there being a kitten in the first place behind the curtain. So I'm going to introduce a Bayesian way of thinking about Bayes' rule and Bayesian statistics in three different ways. These are three ways that they're sometimes taught. I think the first way is probably the most common way, but is probably somewhat confusing. The second way might jive with you, but you might also find it confusing. Hopefully the third way makes some sense to you, or at least one of these ways makes some sense to you. So the usual way would be something like this. So we say you test positive for a rare disease that affects 0.1% of the population. And you have some test that correctly identifies 100% of people that have the disease. The test incorrectly identifies 5% of people who don't have the disease. What's the probability you have the disease? Remember, the disease is very rare. The test is perfect if you have the disease and you tested positive. So your turn, think about this for a second. You tested positive, the test correctly IDs 100% of people who have the disease, incorrectly identifies 5%. What's the probability that you have the disease? I'll give you 4 options here. You're welcome to put your guess into the chat. We have one for C, one for D. Any other guesses? DBD, 2 for D. So let's look at this visually. So you've got 1,000 people, 0.1% have the disease, so one person has the disease on average. 5% of the remaining people, about 50 people, falsely test positive. So shown here at black. So 1 in 51 people who test positive have the disease, so about 2%. So D. So if we were to plug this into Bayes' rule to come up with that, Here we're saying the probability of our hypothesis, so you have the disease, given the evidence, which is that you test positive, is equal to the probability of a positive test given the disease times the baseline probability of the disease divided by all the ways that you can have a positive test, so the probability of a positive test. So if we break that down, the probability of a positive test given the disease is 1.0, is perfect. The baseline background probability or prior probability of disease is quite small, 0.001. The probability of a positive test is all the ways that you can test positive. So you can either have the test and test positive, have the disease and test positive, or you don't have the disease and you test positive. And that works out to 0.1963, which is about 2%. But bonus challenge here, why is this not exactly the same as 1/51? Well, the reason is that it's not exactly 50 people who would test positive, because it's 5% of 999 is not exactly 50, it's slightly less. So that's why it works out to not quite the same thing. Okay. If anyone at any point in time wants to ask any questions, please just, you can put your question in the chat. You can raise your hand. I should be able to see you. I have a second screen open here on my left. And if I don't see you, please just pipe up, or someone else pipe up and let me know. So a second way of thinking about this is something called the Garden of Forking Data. And this is in the book Statistical Rethinking by McElrath. So Richard McElrath here has this great book. There's several editions of it. He also has an online course. He's recorded the lectures for this course. They're on YouTube. Excellent resource. And the slides for this little section come from that course that he teaches. So one of the things he says is that you can count all the ways data can happen according to assumptions. Assumptions with more ways to cause data are more plausible. So imagine we have a bag of marbles. And we know that this bag contains 4 marbles. And so the marbles are either white or blue. So the possible contents, you could have all white, 1 blue, 2 blue, 3 blue, or 4 blue. And you pick out a marble 3 times, each time putting the marble back in and then picking out another marble. And you ask, what is the probability of each of these possibilities given your observation of a blue, white, and blue? So if we have a conjecture that there is 1 blue marble, and we make our first observation, well, the ways that we could have got that are shown here on the bottom in this sort of forking diagram. Could have been blue, white, white, white. We could have picked the blue. And then for each of those possibilities, we can then look at the 4 possibilities again, given the conjecture. And again, for our third draw, given the conjecture. Those are all the ways that we could have drawn, given the conjecture of 1 blue. And 3 paths on this forking diagram are consistent with the data. They would have produced blue, white, blue. And so that's what we just showed there for that conjecture of 1 blue. If our conjecture is that there are 2 blues, this is what that forking diagram would look like. And if our conjecture was that there were 3 blues, this is what the diagram would look like. And of course, it would be impossible to have 4 blues because we observed a white. So if we count the number of those forking paths that are plausible, you come up with 3 ways if there was 1 blue, 8 ways if there were 2 blues, 9 ways if there were 3 blues, and 0 ways if there were all whites or all blues. So what we've basically done is come up here with a likelihood for these observations. So what if we were to draw 1 marble again, and this time it's blue? Well, the ways to produce 1 blue are shown here in that second column. There's lots of ways. There's 4 ways to create it if they were all blue, and so on. And we have our previous counts. And if we want to then update our likelihood, all we have to do is multiply this new likelihood for this new observation by our likelihood of the previous 3 observations to come up with our new possible ways of creating those data. So we've updated the likelihood. So we can also use other information. Say the factory tells us that blue marbles are rare, but every bag contains at least one, and they give us this factory count. So this is the proportion in the factory that have this many blue versus white marbles. And if we want to include that into our likelihood, again, all we have to do is multiply it by our previous likelihood to come up with our new set of possible counts. And if we go back just to that first set where we've got those 3 marbles, for this, to kind of finish this example, the unglamorous basis of applied probability is that things that can happen more ways are just more plausible. And if we turn this likelihood into a probability, what is called plausibility here, simply by taking the ways that we could create the data and then dividing by the sum of all of the ways we could have created these data, we come up with our probabilities. So for that first set of observations with those 3 marbles, this is what we have. We have a probability of 0.15 of there being 1 blue marble, 0.4 of there being 2 blue marbles, and 0.45 of there being 3 blue marbles. So plausibility is probability. It's a set of non-negative real numbers that sum to 1. And probability theory is just a set of shortcuts for counting the possibilities of the ways that you could create the data that you observe. Okay, so are there any questions on that? All right. So we're going to go into some code, and this is what I had you collect your water and land for. So let's just take a pause here and make sure people have the files if you want to follow along here. So again, you need to download the repository. From here, you would click code, download zip, and then open the zip file. And in the folder, I will navigate to that folder for you here on my computer. I'm assuming if you're using RStudio, that's what I'll use today. You should see a Bayes-course.rproj. And if you double click that, that should open up the RStudio project, which will set the working directory to wherever the Bayes course is, or you can open it in whatever else you work with. Just set the working directory to your Bayes course folder. I will zoom in here. Now, this is optional, but I'd recommend you go into the make00 make-exercises.r file. I have some code here that's just going to go through all of these RMD files, and it's going to copy them into a subfolder called exercise files. So if I run this, what that's done is copied all those RMD and there's a couple R files into this exercise files folder. And this is all the same as before, but there are some lines that have exercise after them in comments that have been removed, so that when we go through them like this, the answers are just removed, so you can think for yourself and work through this. But of course, the original files are all back in the original folder. And if you prefer, you are welcome to keep that in front of you and work with the one that has the answers there. So 2 options there. We are going to start with the smallworld.rmd file. I'm going to make this full screen. Is this large enough for people? Have I zoomed in enough? Yeah, okay. Actually, I guess I can see on the other screen. Maybe that's a little better. Okay. So what we're going to be doing is going through a Bayesian approach to exploring a one-parameter model. And we're going to do that with something called a grid search approach, which I think is a really intuitive way to sort of get introduced to the ideas of Bayesian probability. It just doesn't scale very well to complex problems with lots of parameters, but it works really well for 1 or even 2 parameters. I'll start by just running this chunk of code to load ggplot and dplyr and set a ggplot theme. I had you before go and spin the globe here. When we did this in class, we threw a beach ball around the room. That was a globe. And these are your data, which I hope I have faithfully transcribed. I may not have. You probably have a previous set of data in there, and that's just fine for this exercise as well. You don't necessarily need to have this exact data set. But these are the data that we collected, with 1 being water and 0 being land. And we are going to calculate the proportion of Earth that is covered in water based on these data. So we've got a bunch of 0s and 1s in DAT. And to do a grid search, what I'm going to do is I'm going to create a sequence of values that I want to evaluate the likelihood at. So I'm going to evaluate at a whole bunch of proportions. So that's what P is going to be here. It's just going to be a sequence from 0 to 1 with very small increments. To start off with, we're going to have a simple uniform prior. So we're going to say that the probability could be anywhere between 0 and 1. I'm going to run that line. Run a line of code here just to make sure that my prior adds up to 1. So if we look now at sum of prior, it adds up to 1. Prior is a whole bunch of small numbers for each possible value. And then I'm going to iterate through my data. And for each data point, I'm going to calculate, I'm going to use this function dbinom, which calculates the likelihood from the binomial distribution, given that many, to have seen that many waters, given that probability that I'm checking. We looked at Bayes' rule before. For Bayes' rule, we take the likelihood and we multiply it by the prior. We normalize it so it sums to 1. And we looked at that plausibility before with the garden of forking paths. And then we're going to record it. And we're going to do that for each data point. And let me just run this now so you can visualize what we're doing. So what we've got here now is each one of these cells here in our facet wrap ggplot is a new data point that's been added to our observations. And in each one, gray was our prior probability, and red is our posterior probability. And then for the next data point, we're going to take our previous posterior and make that the prior. We're going to add another data point. So here the red becomes the gray, becomes the prior in our sort of next observation. And then we're going to update our posterior. So now our posterior is the red becomes the gray. We add another data point. In this case, it must have been water. It gets pulled towards 1. And then another data point. This one must have been land because it pulls it towards 0. And fifth observation, and so on. And over time, we start centering over some value, and the prior and the posterior for each data point become closer and closer and closer. And we start ending up with a posterior distribution that starts to close in on what our estimate is. Here, somewhere around 60% or something. We don't have a large sample size, and our online spinning globe may be slightly biased and hard to use. Does anyone know what the true value is for the proportion of water on Earth? I'm going to switch back here. This is from the previous time when we taught this course last week, and it's actually a little bit closer to the truth. The true value, yeah, it's 70-something%. I think it's 71. So last time we did it, it worked out quite well. This one is a little bit biased towards land. But it's pretty close. So our experiment, our randomness was spinning the globe. We took 22 observations, and this is an example of Bayesian updating. So data point by data point, we're adding a data point to our posterior distribution. And what was our posterior from the previous data point becomes the prior for the next data point. And we slowly see our posterior evolve over time. Are there any questions about that? The shape of this is coming from the dbinom function, which is giving our binomial density. So I'm going to give you just a a minute or two just to go into this chunk of code. I encourage you to try some different priors and run the code again, run the chunk of code again, and look at what changes. You can think about these questions. What effect does changing the prior have on the posterior for the first few data points? Does the posterior end up in a qualitatively different place with different priors above? So I'll give you a minute to experiment with some of these priors. You're also welcome to code in your own prior if you'd like. Starting with a binomial prior that resembles sort of roughly where I think we're going to end up. If we start with something more extreme, let's see. So here's an example where I've set binomial prior with that's really, really tight initially. And so the data that we give it really aren't enough to move around the posterior very much at all. Here I'm using a beta distribution. And again, this roughly reflects what we know to be roughly the right answer if we were to guess beforehand. And so what it means is that in the first few data points, our posterior jumps around less and is more reflective of where we think it's going to end up, versus having the uniform prior that we started with. And if I run that chunk, so there's no information in our first step, and so we've got a first observation must have been a water, and so it gets quite extreme like this. And then you've got a water and a land, so now it's 50-50. So our posterior is getting pulled around more because there was no prior information, and it's considerably wider at the beginning. Over time, it gets narrower and narrower and narrower. So that is an example of Bayesian updating, where every single new observation, we recalculate our posterior probability using the previous posterior as our new prior, which is what we can do with Bayesian models. But probably a more common way to look at this would have been to fit all the data at once. So we can do that in the next chunk. This n is going to be used just for sampling from our distribution afterwards, but otherwise this is going to be the same as before. So I'm going to use this uniform prior. I'm going to calculate my likelihood. Here I'm using the size argument for the density of the binomial likelihood in order to run all my data at once. Then I'm going to calculate the posterior as the likelihood times the prior, like I did before. And I'm going to normalize my posterior so it sums to 1. And then I'm going to plot it. And now we have our prior, which was the gray here. So we have this uniform prior to start with, and we have our final posterior. So this should be the same as the red shape here after our 20-second data point was added. But the difference is that we have done it all at once. So this might be a more typical way of running Bayesian data analysis, but there's no reason why you can't update. So throughout this course, a lot of what we're going to be doing, and most of what we end up doing with Bayesian data analysis, is summarizing samples from the posterior. We'll talk a bit about why that is when we talk about MCMC. But as sort of a segue into that, one of the things we can do with this type of grid search approach is we can sample from the posterior that we have calculated. And to do that, all we have to do is sample from our proportion waters that we have proposed, the P's, probability equal to this posterior, which is the values that create this red curve. And I here am going to take 2,000 samples. I'm going to have to say replace equals true because we have, I believe, far fewer than 2,000 values of P to sample from. So if I do that, what I now have should be values from our P, our proportion water vector, that are sampled in proportion to the posterior probability, so in proportion to this red curve here. So we can now take those and shove those into ggplot just to come up with a histogram of what we just did. So we've turned that grid search sort of perfect calculation of the density distribution into a stochastic sampling from that distribution. So here the count is the number of samples for each of these, within each of these bins that ggplot has made in this histogram. So once we have these samples, there's lots of things we can do with them, and we'll do this throughout the course. So to warm up to this, we can do things like we could take the mean of our samples. And if we do that, I'm going to take the mean, I'm going to take, and I put a line here, so that's the mean of our samples in black. Or I could take the median here with a dashed line. We can also calculate credible intervals. For this, one way you can do that is use the quantile function. So in Bayesian data analysis, we usually call confidence intervals credible intervals. And this is a quantile credible interval. So I'm going to take the 0.1 and 0.9 quantiles, which gives me a 80% credible interval. So in this example here now, we've got the quantile credible intervals, which means that 10% of the probability density is below this value, and 10% is above this value, and 80% is between these two lines. So that's what a quantile credible interval means, and we can do that at any probabilities that we wanted to. There are multiple ways to calculate credible intervals. I think quantile is probably the most common, but another one is called the HPD, or highest posterior density interval, which is defined as the shortest possible credible interval with the appropriate probability coverage. It's harder to calculate, so we'll rely on existing function. So there's a function in CODA called HPD interval, which will calculate it for us. And let's do that and plot it. And so that's what I'm showing here in the dashed line. So this is basically saying what two lines can I draw on here that are the closest to each other, in which 80% of the samples, or 80% of the posterior probability is between them. So it's the region by which we are, the smallest region by which we are 80% confident. So it's the smallest possible 80% credible interval. To do that is a little more complicated. You can either iterate through all possibilities, or often it's done by fitting some kind of a curve to the samples and then calculating it based on that. Andy Edwards at Pacific Biological Station actually just had a paper out, I think in Fisheries Research, maybe a month or two ago, which was on proposing that maybe we should use highest posterior density, or HPD intervals, more commonly in fisheries science, especially for things like recruitment deviations. They can give us a region that is considerably smaller and thereby, reduce perceived uncertainty. But they don't have the same intuitive meaning in that it's not 10% below and 10% above. So if I told you this is the 80% HPD interval, that doesn't give us information about how much probability is below or above it, which often we do want to know, say in stock assessment contexts, when we're doing things like wanting to know the probability that we are above or below a reference point. For that reason, I think quantiles often make sense in that context. So we can also calculate a one-sided credible interval. So here I'm just going to take the threshold above which 20% of the probability density is below. Could have done that with the quantile as well. So instead of picking a given probability threshold, we could also calculate the probability from some meaningful value. So imagine we wanted to know what is the probability of being greater than 50% water on Earth based on our 22 observations. So here I'm going to plot the 0.5. So we're just calculating how much of these samples are to the right of this line. And throughout this course, you're going to see this kind of thing pop up a lot, so it's worthwhile understanding what's happening. These are two different ways of calculating that. And the shortcut is to take the mean. And the reason this works is because if you take a logical in R, so if I ask for what are all the posterior samples that are greater than 0.5, I get a bunch of trues and falses. R treats trues and falses as zeros and ones. So if I take the mean of this, I get the proportion of these that are greater, that are true, basically in this case. So the proportion that are greater than 0.5. So it's the same thing as taking the sum of all those that are greater than 0.5 and then dividing by the total number of samples. So a shortcut is to take the mean of some logical vector, and that gives us how much of this density is to the right of our line. So in this case, we're saying there's about an 80% or 0.8 probability that there's more than 50% water on Earth based on those 22 samples. And of course, we're not limited to something like that. We could say something like, what's the probability that there is between 60 and 80% water? So to do that, I just create a vector with two logical statements. So I need the posterior samples to be greater than 0.6 and posterior samples to be less than 0.8. So if we run that, we get a whole bunch of trues and falses. We take the mean of that, and in this case, it's about 43%. So what we're saying is that based on our posterior, 43% of the density is between these two lines. So what we've done here is just, we've done full Bayesian data analysis, but we were able to do it with what's called a grid search approach by just taking a sequence of values to evaluate our one parameter at. We've then taken samples based on that grid search approach, and we've summarized those samples in various ways. This works really well for one or two or maybe even three parameters. When we get up to actual realistic models, this sort of falls apart because you end up searching over such large grids. This becomes computationally very hard, but it's a great way to visualize what's going on. Are there any questions on this before we return to the slides? So let's talk a bit about what makes Bayesian methods different in a practical sense. So one thing you might hear is that only Bayesian analyses use priors, and this isn't exactly true. Maximum likelihood frequentist methods can also use priors, although they are usually called penalties in that context, but they're really the same thing. And Bayesian sampling methods can be applied without explicitly defining priors. The truth is that Bayesian methods almost always include priors, and frequentist methods rarely do. There is also a difference in focus. Maximum likelihood methods tend to focus on point estimates and characterize uncertainty via the curvature of the log likelihood surface. Bayesian methods tend to focus on exploring the full parameter distribution. There's differences in perspective. Frequentists usually think of probability in terms of long-run frequencies. And Bayesians usually think of probability in terms of degree of belief. But these two things they work out to the same thing in the end, but they're just a difference in perspective. There's differences in focus. Maximum likelihood tends to focus on predicting expected values, usually means. Bayesian methods tend to focus on predicting new observations. And we'll come back to this several times when we talk about predicting from Bayesian models. Both methods can predict both new observations and expected values, but what you're used to seeing, say if you're running a linear regression or a GLM and R, is you're usually used to predicting an expected value and an uncertainty on that expected value. Bayesians tend to focus on predicting new observations and uncertainty on new observations. The actual core difference between them is that frequentists think of the data as being one of many random trials, and the data being generated by unknown but fixed parameter values. And Bayesians think of the parameters as having some probability distribution and the data as being the one real and fixed thing. So coming back to this proportional Bayes rule, so you've got the probability of the parameters theta here, and theta is often used to mean all of the parameters in some model. So the probability of the parameters theta given the data observed is proportional to the probability of the data given a set of possible parameter values multiplied by the prior probability of those parameter values, theta. So this is Bayes' rule, and a common way you'll see it with theta and data. The thing on the left is the thing that we are calling the posterior, and that's proportional to the thing we call the likelihood. So this was the d binom that we used in that small world example with a portion of water. And then the probability of the parameters is what we called the prior. And maximum likelihood methods focus inference on the likelihood part, and they sometimes add a prior, but they're focusing on the right side of this equation. And Bayesian methods focus on the left side of this equation. So to get to the left side, we have to do all the stuff on the right side first. Likelihood times the prior, and then we have to divide that by all the ways you can have the probability of data. And this is the hard part. The hard part is to normalize the thing on the right to turn it into a probability distribution for the left. So maximum likelihood works with sort of an unnormalized version on the right, and Bayesian methods turn that into a full posterior distribution by normalizing it so that the probability distributions sum to 1 for the parameters. And we can do this hard part by doing the math, which is hard for most applied problems, but can be done for simple problems. We can use methods that approximate the shape of the posterior. So INLA, the integrated nested Laplace approximation, R package is an example of this, where it approximates the shape of the posterior and it does calculations to maintain that posterior throughout the calculations. Or we can take samples from the posterior and summarize those samples, like we did through that proportional sampling in the small world example, and like we're going to do with MCMC. And that's, I think, the bulk of applied Bayesian data analysis is through taking samples from the posterior such that the samples are draws from the posterior so that they are in proportion to it, so that they automatically sum to 1, and we can turn the thing on the right to the thing on the left without doing the hard part in the denominator on the right. So why go Bayesian, or why not to go Bayesian? Well, I think my first rule will be it's never wrong to go Bayes, but sometimes Bayesian methods will be really slow. So for really big data sets, some spatiotemporal models, which is a lot of what I work with these days, Bayesian methods can be very slow, and maybe you just don't have the patience. Sometimes the added model complexity isn't worth it. So say for a quick linear regression with lots of informative data, little prior information, no desire to talk about the effects probabilistically, maybe it's just not worth the trouble because there's extra things you have to report in terms of sampling algorithms, whether things converged, and so on. Also justifying any priors you used and reporting on the sampling algorithm. When does a Bayesian approach really shine? I think they really shine when it's helpful to talk about the probabilities on parameters or predictions. So a frequentist confidence interval is defined as, say, if the experiment was repeated 100 times and each time we calculated a confidence interval, 95% of those confidence intervals would contain the true parameter value and 5 would not. Whereas a Bayesian credible interval says there's a 95% probability that the parameter value is within the credible interval, which I think for most people is a much more intuitive way that we want to think about confidence intervals, and that is what a Bayesian credible interval is. Bayesian methods really shine when incorporating priors is useful. It's when you have some prior information, either from some previous studies or some domain level knowledge. And I'd argue that we almost always have some level of prior information, but it can also help constrain our estimation to come up with more sensible answers. They really shine when it encourages you to think about the model structure and what it all means. They really shine when you want a straightforward way to propagate uncertainty to or from another analysis. When you're willing to wait a bit, so we're talking maybe a couple seconds to 2 hours. or maybe days, but at this point, we're usually talking seconds to hours. When you want a way to simulate new observations that incorporates all parameter uncertainty, not to say you can't do this with a maximum likelihood model, but it's more straightforward because it's built into the generative model that you build while fitting a Bayesian model. So, some goals for this course. I'm assuming you have some familiarity with linear regression and generalized linear models, or GLMs, and ideally mixed effects models, although we'll only really touch on those towards the end. I'm assuming you have plenty of experience in R, and you may or may not have had exposure to Bayesian methods in JAGs, bugs, STAN, etc. What I hope is that you'll gain a high-level understanding of fundamental concepts in Bayesian data analysis and Hamiltonian no U-turn sampler sampling. You will gain some exposure to R packages like BRMS, STAN, and other tools that are built around these packages like Tidy Bayes and Bayes plot. You'll feel less intimidated about Bayesian approaches, and you'll know where to go for more information. You'll feel empowered to seek out that information to use Bayesian data analysis methods in your own work. So let's talk a bit about Markov chain Monte Carlo, MCMC. So although it's a kind of long and intimidating set of words, it really is fairly simple in what it means. So a Markov chain in statistics is just something where your next step is only dependent on where you were at a previous step. So it's just a chain. And the Monte Carlo part basically just means that there's you're sampling, there's randomness, and using sampling to get at a parameter distribution. And that the guy who invented this idea of Monte Carlo sampling is Stanislaw Ulam. You may recognize the name Stan. That is what the software Stan is named after. And I believe he named it Monte Carlo after his uncle who liked to gamble, is what Wikipedia tells me. So you can think of MCMC in several ways, and I'll give you sort of a complex to a simple way to think about it here. So the Wikipedia definition is that it's a class of algorithms for sampling from probability distributions based on constructing a Markov chain that has the desired distribution as its equilibrium. You could also think of MCMC as an algorithm for proposing and accepting or rejecting possible parameter values, so at the end, all the parameter values that you saved represent the posterior distribution. MCMC is also just a way of sampling from the posterior distribution without extensive calculus or ridiculous computational power. Or if you really need to, you can just think of it as a black box to do Bayesian statistics. So why do we need MCMC? Well, we need it in order to get at our samples, to do that hard part we talked about in the denominator, to get at a proportional posterior distribution that is normalized to sum to 1. And MCMC can be very simple. So if we go through the steps of Metropolis, Markov chain Monte Carlo, which I think would be the simplest form of MCMC, we can write out this in 5 steps, and we will code it ourselves in R after this. So if we're talking about a parameter that we're sampling from, we have to pick a point in our parameter, a parameter value to start from. So that's our starting point A. We have to propose a new point B, and this is usually proposed from a normal distribution or a multivariate normal distribution with some standard deviation. We evaluate the probability at both point A and at point B, so both the likelihood and the prior combined. If the probability of point B in our parameter is greater than the probability at point A, jump to point B. If the probability is less, you still want to jump sometimes, so we jump in proportion to the probability of B divided by the probability of A. And that is it. And you repeat from your new starting point. You do this over and over and over. That is the Metropolis-Hastings MCMC algorithm. So think for a second about why you need to do step 5. So the reason is that if you didn't do step 5, your algorithm would just work its way to the point of highest probability density and it would just get stuck there. And that is effectively what you're doing when you optimize a maximum likelihood model. You're trying to find the point of maximum likelihood or minimum negative log likelihood. but we want to actually sample from the distribution. And so to do that, we don't want to get stuck there. We need to sometimes jump away. And it's the step 5 that sort of is the magic behind, meaning that our samples, all the accepted samples, are proportional to the posterior distribution. So let's do that in R ourselves to look at it. So we have a file mc02 mcmc demo.rmd. And we are going to start by simulating some data. So I'm going to set the random seed generator so we have the same data. Our simulated data is going to have a mean of 1, so mu. It's going to have a standard deviation of 2. And we're going to pretend we know that just to make this example really simple and of 1 parameter. And so if we plot our data, we're going to simulate data with our norm. We end up with 50 observations that look something like this. So we're just sampling from a normal distribution with some mean and standard deviation. And what we're going to do is write our own MCMC algorithm to estimate the posterior distribution on the mean. So I'm going to start by creating an empty plot to track our MCMC chain. So I've got mu here on the y-axis because that's what we're sampling. I've got my chain iterations here on the x-axis. I'm going to choose my jump standard deviation. So that's going to be how I make proposals, as we'll see. And this becomes the one thing that is sort of important to tune and can affect how our MCMC behaves. We'll look at that after. I'm going to record my iterations. So I'm going to start on iteration 1. I'm going to start with a proposal value of 0. And I'm just going to set the seed here to make sure we have the same MCMC chain. The way I've set this up, we're going to work through this. These are the 5 steps we saw on the slide. And if we run this chunk, it is going to plot one value. Here, our starting value. So let's go through this code. So we have our starting value, which in this case is our previous proposal, was 0. And we have our jump standard deviation that we have chosen, which defines how our algorithm is going to work. I want to create one proposal because we have one parameter here. So I run this, and if you put parentheses around a line of our code like this, that also puts the result here in the console. I'm just going to run this again to go back to the same seed value. So we have our proposal is negative 0.56. So that's our point B. Our point A was our previous proposal, which is where we started. Now we need to calculate the data likelihood of our proposal and our previous value. We're going to do this in log space because these values can get really, really tiny. So log space preserves the numerical precision, and multiplying in natural space is the same here as summing in log space. So we're going to sum the log likelihood for our proposal value given our known sigma standard deviation. So if I run this and this, that's the sum of the log likelihood for our proposal and our previous value. We do the same thing for our prior. So we're going to put a prior out here of a mean of 0 and a standard deviation of 5. Those are our prior values. Now, because we're working in log space, we can just add those instead of multiplying them in natural space. So I'm going to add those to come up with the log posterior of the proposal and the previous value. I'm then going to calculate the ratio of the two, which can be done like this. I can take them into natural space and divide one by the other. This can be dangerous because you can have lose numerical precision. So instead, I'm going to keep them in log space and subtract, and then exp the result, which will give me the same answer whilst doing that without taking them out of log space. So here is our probability ratio. And if this is greater than 1, of which this is not, then we're always going to accept the new parameter value. If this ratio is less than 1, we're going to accept the parameter values in proportion to the ratio that we've calculated here. So to do that, this is just a fancy trick to do that. We're going to generate a random number between 0 and 1. And if this is greater than 1, this will always be accepted because it'll always be true. And if it's less than 1, then it will be in proportion to this ratio. So if we run this, in this case, we ended up retaining the previous value. We didn't end up accepting the new value. So we stayed where we were. We then plot our value and we increment our chain by 1. I'm going to go up and I'm going to click this button in our studio just to run this chunk over and over and over. So this time we proposed a value that it did jump to. It moved again, moved again. This time it rejected the proposal, stayed where it was, accepted, rejected, rejected, accepted, and so on. I'll just run through this. We're running our MCMC, Metropolis-Hastings chain. And there we go. So we've got 31, I think, iterations of our MCMC chain. And so if we do something like plot on here our true known value, because we simulated from a known distribution, it was 1. Our samples are indeed sort of oscillating generally around our true distribution. So if we did that enough times, and theoretically we'd have to do it infinite times, but at some point it's good enough, and we'll talk about that later, we then have samples that we can use to represent our posterior distribution. So what I've done next is embed that same code from above into a function, defining a function here with a mu, the true mean, the true standard deviation, number of data points, and then a prior mean and a prior standard deviation, a jump standard deviation, how long our MCMC chain should be, and then what seed we want to use. And by default, it's going to sample a random seed. And then all the stuff in here is exactly what we saw above. This just lets us wrap it in a function so we can call it easily. So I'm going to run this chunk. So now we have our MCMC example function. Scroll down. We can call it like this with our parentheses on the end. And what I've done is create a little manipulate call to this function. And manipulate is it's an old school version of Shiny, if you're familiar with that. It just lets you work within RStudio. This will only work within RStudio. And it creates this little gearbox here, which lets you play with the various arguments that I've given it here in the manipulate call. So we can now ask questions. What happens to the posterior as the number of data points gets large? So as I increase the number of data points here, posterior gets more and more narrow, right? As our get more and more certain about the mean. So here we're seeing the observed data in the first panel. This is our MCMC sample. Here I've got 1,000 iterations. The red is our true known mean. In the final panel here on the right, we have the prior distribution I'm showing with this curved line. The true mean is the red, and then the histogram are my samples. So when I had very few samples, I end up with a fairly wide posterior. If I have a lot of samples, it gets quite narrow. If it gets really, really small, then I end up with a fairly uncertain posterior that starts to look more like the prior. If the observation error, let's put this back up to something sort of in between. If the observation error gets really big, then it gets more the estimate of the mean gets more uncertain. If the standard deviation gets really small, then our uncertainty on the mean gets smaller. And then the important thing here is really about the tuning. So I've got this jump standard deviation. So this is how big a jump should we make on each proposal from our previous value. So it's starting here, I think, at about 5. So if this gets really big, let's increase our number of, if this gets really big, basically we make a lot of really bad proposals, and so we don't tend to move around a lot in the chain. We sort of get stuck. And if this gets really small, then we can make good proposals, but we sort of end up stuck in one place because we don't wander around the posterior very well. I think this is actually going off the bottom of my screen. Let me just increase the number of so reps length of our MCMC chain, 1,000. Yeah, reps is off the bottom of my screen, so I can't see it. But let's change the default to more samples so that I can run this. So now I've just created more samples. You should be able to see them off the bottom of this manipulate thing, but I'm too zoomed in. So if we make this really tiny, here's such a simple problem. We don't really end up with a issue. Well, if we get this really, really small, sometimes we don't actually get to the true distribution because our proposals are so small, we haven't wandered yet up into the true distribution. And if our jumps are really, really big, there's a lot more instances where we make a lot of rejections. So we end up with more autocorrelation and we end up with less independent samples of our posterior. So with the Metropolis-Hastings, there's one thing to tune, and we need to get this jump distance about right. And as long as it's about right, we end up with a nice set of samples from our posterior that are fairly independent and nicely shaped posterior distribution. Too big or too small, and it doesn't behave as well. So what we looked at was the simplest form of MCMC, Metropolis-Hastings, MCMC. And now we're going to transition to talking about Hamiltonian and the NUTS MCMC, no U-turn sampler MCMC, which is what is used in STAN. And although it's still just an MCMC algorithm, there is quite a jump in complexity, but all we're doing is making those 5 steps a little more complex, but the idea is the same. So a caveat that this is mostly for interest's sake. You don't need to understand most of this to use STAN, and I'll tell you what you need to know at the end. So a lot of these figures here are taken from this preprint by Michael Betancourt, who was one of the people that coded the sampling algorithm in STAN. He has several preprints, many of which are probably pretty hard to read. This one is moderately readable, and it's a conceptual introduction to Hamiltonian Monte Carlo. And so he says, imagine a satellite orbiting Earth in Earth's gravitational field. So that's what we see here. And if you have too little or too much kinetic energy, the satellite will crash into Earth or fly off into space. Similarly, we could say too little or too much kinetic energy and our sampler will crash into the posterior mode or fly away from our posterior. But if you get it just right, the satellite will stay in orbit indefinitely. Similarly, if we get it just right, we can have an MCMC sampler that stays sampling indefinitely and therefore has the properties of an MCMC sampler that you're sampling in proportion to the posterior. So Hamiltonian Monte Carlo is all about dynamics of movement in space with kinetic and potential energy. And I'll see if I can get this to work.
And so maybe, oops, you can get one thing to orbit another. Oh. I think I can do a little better. There we go.
Oh my God.
So the Earth-Moon system, maybe?
So this is an analogy that comes from, I think, originally one of Einstein's books, where he tries to portray the idea of gravity by thinking about having a bowling ball on a trampoline and then throwing a marble, and the way that the marbles orbit around that bowling ball is analogous to how a moon orbits around a planet. And the dent in the trampoline is reflective of the dent in space-time that causes that. And the equations that are used to calculate how that marble would move, assuming no friction, or how planets orbit, is what is Hamiltonian dynamics. Go back. So in that example there with the trampoline reflects our negative log probability distribution. The ball is our sampler, and we want to sample by repeatedly rolling the ball, starting each time from where we stopped it last time, because we have a Markov chain. But we need to pick how hard and in what direction to send the ball. So that's all fine and well, and theoretically, Hamiltonian sampling would work something like that, but the problem is doing this in practice. We have to numerically calculate the trajectory. And simple numerical methods tend to accumulate errors and diverge from the theoretical path. So here, the arrows are the sort of the theoretical trajectory that say a moon would be orbiting around a planet, or a satellite would be orbiting around Earth. And the red line with a circle on the end, that is the true trajectory along one of those paths. But with a simple numerical integration, we end up with calculating a path in the green that deviates from the truth. So they tend to accumulate errors, and simple numerical methods don't work very well to approximate that path. So we need some way to know that that is true and some way to calculate it numerically in a way that doesn't accumulate errors. So how do we know that we've diverged? Well, kinetic and potential energy should be conserved. So on the right here, we have a plot of potential and kinetic energy. If we sum those up, total energy should be constant. And so we know that if the total energy in the Hamiltonian equations starts deviating, then we have a problem. We've diverged from the path. So one of the breakthroughs in the STAN package was developing what they call a leapfrog integrator that can do these calculations and oscillate around the theoretical path instead of accumulating errors and diverging, shown here with that green set of lines. And in this numerically calculated path, we need to choose how large or small those steps should be, how many steps to take. These are actually reversed. Sorry, how large or small the step should be the adapt delta. How many steps to take, the solution is the no U-turn approach. And then what momentum or kinetic energy to start with, the solution is to sample from something that in Hamiltonian MCMC is called the mass matrix. So let's break down those various parts. So the no U-turn algorithm, this is from the paper that first introduces the no U-turn sampler by Matt Hoffman and Andrew Gellman in 2014. So what we're looking at here is the, what they call the set of, each one of these is a proposal basically. So we've got our starting point. We run our Hamiltonian dynamics forward in time for a set length. That's the first step here. And then we randomly choose whether to run our dynamics forward or from backwards in time to where we are currently. So that's the next step. And we double the chain length. So this time it was randomly chosen to start backward in time and run the dynamics that way. Then we double the length again, randomly choose forward or backwards in time. This time it's again backwards in time, and so on. And so the number of times that we do this, where we choose to run our Hamiltonian dynamics for twice as long as the last time, is called the tree depth. So tree depth of 1, 2, 3, 4 here. And you can see that as you increase the tree depth, you have a lot more calculations to do. So there's a maximum tree depth where Stan stops doing the calculations. You may get a warning that you've hit the maximum tree depth because of that. But that's the gist of it. So you need to know when to stop sending out those trajectories. And where the no U-turn sampler comes in is to tell you when it thinks that the path that it's calculating is starting to fold back on itself. And so it's not a good use of computational time to continue, and you should stop and evaluate your proposal there. So in this figure from that paper, which I only really understand parts of, the important part here is that it's calculating this trajectory here, and at some point, the trajectory where you see the blue arrow and then the pink arrow, that's the continuation of where the path was going, that it has folded back on itself to an angle that is less than 90 degrees. The no U-turn criteria is met, so it stops calculating those trees and it evaluates the proposal. So something else we need to think about is the equivalent of that standard deviation in the normal distribution that we used for the jump distance in Metropolis-Hastings MCMC. And Hamiltonian MCMC would force you to pick these types of things. Lots of parameters actually in the Hamiltonian dynamics, but the no U-turn sampler simplifies this by really boiling it down into generally one thing that you can toggle, which is this thing they call adapt delta, which is the target acceptance rate. So if we go back to that Metropolis-Hastings example and we kept track of how often did we accept versus reject our proposal, the average of that would be our acceptance rate. And the default in Stan is 0.8, so it's trying some various tuning parameters during a warm-up phase, and then it's trying to find a place where it's going to have about 80% acceptance. And you could increase that, and we'll talk about that later, but sometimes you might increase that towards 1, which is going to make generally smaller proposals, so it has a higher acceptance rate at the expense of making smaller jumps and traversing the posterior distribution more slowly. But an important part to all of this is that there is a warm-up phase in Stan, and therefore we cannot use samples from this warm-up phase because they are not true MCMC samples that are representative of our posterior. So in some other sampling algorithms like Metropolis-Hastings or Gibbs, if we don't have this warm-up phase, we usually discard some of our initial samples just to discount the effect of where we started in parameter space. But it's more than that in Stan. There's both an effect of where we started, and the warm-up samples are used to tune the Hamiltonian dynamics, and so they are not valid samples in themselves. So there's going to be a warm-up phase. In Stan, they like to call it warm-up. Often it's called burn-in with things like JAGs. They don't like calling it burn-in in the Stan world because there is this adaptation phase happening. So you might be saying that was a lot. Good thing is you don't really have to understand most of what I just said. So what are the key things you need to know? Well, Stan uses a fancy sampler called the no U-turn sampler that usually achieves convergence faster than simpler MCMC algorithms, at least for hard problems, like weirdly shaped posteriors, a lot of parameters. That's when the no U-turn sampler really shines. But it's harder, it takes longer for it to make a proposal. You know, it has to calculate all those Hamiltonian trajectories instead of just making a simple proposal from a normal distribution in the Metropolis-Hastings. So each sample takes longer to make, but it takes better samples. And so for complicated problems, it is usually faster. It does this with making better proposals that are more expensive to make. Important thing with that is that you need fairly short chains with the no U-turn sampler compared to something like JAGs or Metropolis-Hastings. You might there have seen people take like 100 million samples. But with the no U-turn sampler, you'll typically be making maybe 2,000 samples. And you might even get away with just several hundred samples. The theory is based on Hamiltonian dynamics, which describes things like how a ball or sampler rolls over a surface, the posterior distribution. The no U-turn sampler needs a sufficient warm-up period to tune the algorithm. You always must discard these samples. And generally, all the functions working around Stan will discard these for you. So you'd have to go out of your way to include them. The main tuning lever that users have is something called adapt delta. As adapt delta approaches 1, it can navigate trickier posteriors at the expense of slower sampling. Usually the default 0.8 is fine. You will get warnings if you need to increase the adapt delta, and we will see some of that later. But the prime one is something about divergent transitions. So there is a great demo I will go to here. So this is a visualization of various MCMC algorithms. Hopefully this will load. There we go. So what we're looking at here in the background here with this sort of faded blue, this is the joint posterior distribution. So a posterior distribution with multiple parameters. That's joint. And the parameter distributions themselves, the true distributions are shown on the bottom and left of two parameters in this line. And then the samples from the MCMC chain are accumulating in the histogram. Let me try and slow down the delay. So this is the Metropolis-Hastings. Each jump is from a multivariate normal because now we have two parameters that it's sampling from, but it's effectively the same thing we coded ourselves in R. So this is representing the jump distance by this circle. We've now gone off the bottom of the screen. Let's try a different distribution. So now we've got a funnel distribution. So I think the red is if it's rejected, and green is if it has accepted. So slowly, we are accumulating samples from our posterior. So let's try a more complicated one here. Let's go to the no U-turn sampler. Let's try, I don't actually know what they've done, the difference between efficient and naive no U-turn sampler is. And let's slow this down a little. So you're seeing those leapfrog steps, trees going off, one direction and the other direction. And then again, the green is if it's accepted, the red is if it's rejected. Each time it's effectively throwing a ball over this surface. You see here it's managed to get down into this part of the funnel down here. And what's amazing is that this algorithm can actually work its way around some pretty crazy posteriors. Like here, I'm going to speed this up a little bit. So here it's going to work its way around this donut shape. And if we did this with Metropolis-Hastings, theoretically, we would eventually sample from the posterior, but it would probably take a very, very long time to do that. But because it's able to do these calculations based on calculations of the gradients of the log posterior and the log posterior values itself, it's able to navigate some really tricky posteriors. Are there any questions about that?
In those animations, is it always the starting value that's getting accepted or rejected for this no U-turn sampler?
It should be the, I guess it's semantics, whether you call it the starting or the next value, but it's the next point in the chain. So proposes a value, that next value gets recorded, or it gets rejected and you stay where you were and you record that value again.
Okay, so it's the one value after the proposal.
It's the proposal itself that can get accepted or rejected. And then the nature of the Markov chain aspect is that you then forget all your previous calculations. You do your calculations again from where you are, and you repeat. So that's the Markov aspect. Yeah, you're working your way along those calculations. Any other questions? One thing you can think about with this funnel, and we'll come back to this later, but this is a very common posterior shape, particularly in any mixed effects models, where, let's see, the bottom here might represent the standard deviation on a random effect, and the y-axis might represent a single random effect value from that distribution. And so as the standard deviation gets really small towards the bottom here, the possible values get really constrained. I probably have that reverse actually. Standard deviation would be on the y-axis and the value would be on the x-axis. So as the standard deviation gets really small, the values get really constrained, and so your single random effect value gets really has a very small width that it could be in the posterior. And the problem with this, as we'll talk about more later, is that if you tuned this MCMC algorithm to work well up here at the top, the same tuning isn't going to necessarily work well down here. Because your jump distance or a number, if you think back to the simple Metropolis-Hastings that works well up here, is going to make a lot of really bad proposals and might never make it down into the tiny posterior down here. Or if you tuned it to work well down here, it might take you forever to sample way up here. So this type of problem, which is common, creates some problems with MCMC samplers. And we'll talk more about that later. There's ways around it. Now we're going to talk about diagnostics for what is a good set of MCMC samples. I have a few slides on this first, and then we'll look at some examples in R. So the issue is that MCMC is only guaranteed to represent the posterior if you take infinite samples. But we don't have infinite time. We therefore need some way of saying that our samples are good enough. And so all these metrics that we're going to talk about are just asking whether or not our MCM samples are good enough that we think they are proportional to the posterior distribution, because we don't have infinite time. So there's different ways we could be asking, are our samples good enough? We might be asking, are the estimates stable? So if I did this again, would I get a similar answer? And are my chains consistent with exploring the full posterior? Because if not, we don't know what we don't know, and we can't trust the results. So there's lots of approaches for assessing what is good enough. Generally, these fall into visualizations, which are always good to make. They help identify lots of problems that you may not see with statistics that we calculate on MCMC samples, but they don't always scale. By that, I mean they don't scale to looking at lots and lots of parameters easily, and they don't give us some quantitative goodness values to report in our results. On the other hand, you have diagnostic statistics, which scale well to lots and lots of parameters. You can look at them quickly. You can summarize them. They give us something to report, but they can hide issues, and particularly any one diagnostic statistic on its own can hide issues. So the reference for all the material I'm talking about here is this paper in 2021. So the things we're talking about, effective sample size and R hat, have been around for a long time, I think since the 90s. But there have been several updates to them, and the versions that we're talking about here are the versions that are embedded in STAN and that are described in this paper. We'll talk about what makes these different. But first, R hat, which is one of the most common ones you'll see. I think it's sort of a future evolved version of the Gell-Mann-Rubin statistic you might hear about. And it asks, did the chains mix well? So values approach come down to 1.0 as the chains mix very well. The current guidance from that paper is that R hat should be less than 1.01 for all parameters. There are many R hats. STAN now uses the one in that paper, which is a rank normalized split folded R hat, which I will break down in a minute. Effective sample size is the other really common statistic. And this is saying, is the effective sample size large enough to get a stable estimate of uncertainty? It's effectively saying, if my effective sample size is 100, it's saying if I took 100 samples from a completely uncorrelated distribution, like if I just sampled 100 values from R norm, that's the amount of information and data I would have. So the values get bigger and they're limited by the number of chain samples. That's sort of the maximum effective sample size you could have. But if there's correlation in the chains, that effective sample size is going to get smaller and smaller. The current guideline in that paper is greater than 400 is suggested for each parameter. In the Bayesian data analysis book, I think they talked about 100 or 200, but 400 is sort of the current guideline. There are many effective sample sizes, and again, STAN now uses a rank normalized split effective sample size split into the bulk, so sort of the central tendency of the samples, and into the tails of the distribution. specifically the 5 and 95% quantiles. So roughly speaking, the effective sample size is a quantity of interest that captures how many independent draws contain the same amount of information as the dependent sample obtained by MCMC. The higher, the better. So I talked about that there's been some updates to R hat and effective sample size. So there's these three things: rank normalization, splitting and folding, and localized. So the rank normalization means that all of the MCMC samples are rank ordered and then squished back into a normal distribution. And this helps with outliers and transformations. So it means that outliers have less effect on the values that are calculated of R hat and effective sample size. And it doesn't matter whether you're working with, say, a log transformed or a natural space or square root or whatever of your posterior distribution, you're going to get the same values because they've been turned into rank order. They've been turned into just a sequence of, 1, 2, 3, 4, 5, 6, 7, up to all of your samples. The split and folded means that each chain is split in half and folded on itself before calculations are done. This helps with detecting drift and changes in variance within an MCMC chain. We'll see examples of this in a minute. And localized means that there are calculations for effective sample size that are done both for the bulk and the tails. So let's look at some good and bad MCMC chains. So this is what you want. I've got lots of chains. I'd say at least 3. The default in Stan is 4. You can always use more. You can run chains in parallel. But we want something that looks like a fuzzy caterpillar like this. Several chains, they look fairly random, they overlap each other. They're not trending over time. They have the same variance as each other. That's what you want. This is also a perfectly fine chain, but you only have one chain, which means you can't necessarily fully diagnose it because you haven't had multiple starting points. Could be that if you had started in a different location, you would end up in a different part of the posterior, which is a problem. Here's an example of that. Here's where I might have started in 2 different starting points. So I've got 2 chains. They start from random starting points, and they are sampling different parts of the posterior. They have not converged on a value. This is the importance of having dispersed starting points and multiple chains so you can detect this type of thing. Now you could also see this in some models where there's a thing called label switching. Dynamic factor analysis is an example of that, where a parameter might be the same thing whether or not you multiply everything by, say, -1 and flip it. And one chain might be in one state and the other chain in the other state. That is sort of a more esoteric problem, but it does appear. But the more common way that you would see this is just that you start in different places and the sampler is not able to get away from where it started by the time you're starting to record your MCMC samples. So this is not good. Here is a highly autocorrelated MCMC chain. So this isn't necessarily a problem in itself. It might be okay, but what it means is we have fewer samples than the total number of samples that we've taken. So our effective sample size is going to be reduced. As long as our effective sample size is high enough, it's okay. You might hear about thinning. Thinning is something that's quite common with Metropolis-Hastings or Gibbs samplers, where you're dealing with tens or hundreds of millions of samples and it becomes computationally burdensome to monitor and save all of those samples. And then thinning makes sense. So you might only save every 10th sample or every 1,000th sample. That's what thinning means. We don't tend to do that with Stan because we're dealing with far fewer samples. So there's no computational need to thin. And by thinning, we're always throwing out information. Now, the more autocorrelated, the less information we're throwing out, but we're always throwing out some information. So this just basically in itself means we might need longer chains. This is an example of drifting, which is something that we don't want to see. And in the original calculations of R hat, this would have been okay, but in the new split and folded, where it's split in half here at 500, folded back on top of itself, the chains would no longer be consistent with each other, and the R hat calculations would not look good. Here I've shown an example of what it might look like if you'd split and fold them on top of each other. There would actually be half the number of chains, so it'd be 500, but the same thing. This is how it would look. This is something that you may see frequently and is not a good thing. So here we've got a parameter that is sort of getting stuck in certain parameter spaces. It could be, you probably plot this parameter against some other parameter and you'd see that maybe these two parameters are very weakly identified and sort of one can go to one space and the other can go to the other, and you end up with the same log likelihood. You may need to constrain your model more. This could also happen with that label switching that I talked about, where the MCMC sampler is actually jumping between states, where your whole model is sort of flipped by -1 to end up with the same answer. And it's a tricky thing to deal with. So a few words on convergence. So converged is commonly used to denote stable chains that have mixed well. You can never be 100% sure that your chains have converged, but you hopefully fail to find problems with your chains. And in that case, we can say that the properties of your chains are consistent with convergence. Now, for simple demo models, like a lot of what we're talking about in this course, chain issues may seem trivial, but in real applied settings, chain issues are very common. Do not ignore them. Although for model experimentation, we can often lower our standards while we're building our models and then worry more about getting optimal convergence of our chains for our final model inference. Some solutions to chain issues: we can sample for longer. We can warm up for longer. Because one of the things this does, it can better tune our no U-turn sampler, and it can also improve the mass matrix, which defines the proposal direction and momentum. You can sample with more chains. Increasing the number of chains is roughly equivalent to just sampling for longer, and you can make use of parallel processing in that case. You can adjust the sampler settings. There are some settings in no U-turn sampler that adapt delta is the main one you'd control. You might need to reparameterize your model, and we will talk about that later. You might adjust your priors. You might add more information to your model by increasing the information in your priors, making your priors more constraining. Or you might just be fitting a model that you cannot fit to your data, and you may need to simplify your model. So you can open up 03 MCMC diagnostics exercise. If you open up the one in the exercise files subfolder, if you created that, it won't have the answers. I'm going to open up that one. You'll see here that I've used the here package. Occasionally people have trouble with this, and if that is the case, you can replace that with the path to the data file itself. But if you're not, here is just a way to find the base folder of this project, which works within a RMD, our markdown file, because there's a setting within our studio in our markdown to evaluate chunks in the project, current, or document, and I forget the default, but I think it's different than what I have. I think it might be document, and I have it at current. Regardless, if you use the here function, this should find the root path to the project and then append on that data there. So that's all the here is doing. The colon, if you're not familiar with that, that's just calling the here function from the here package without bothering to load the here package itself. So what I have done is created some MCMC samples. They're fake MCMC samples. And they all have something wrong with them, or some of them are okay. So I've got 4 chains for this parameter I've called theta, and I've got 500 samples for each chain. Now I could just plot that myself using ggplot or base graphics, but we're going to use a function in baseplot, which is quite useful once we have more parameters to work with. And there's a function MCMC trace to make what we call trace plots, which is just these line plots of the our 4 chains. So we've got 500 samples across 4 chains for some parameter theta, each color by default different shades of blue in Bayes plot show our different chains. We can calculate, if this were a model fit from stan, it would print out the r hat and effective sample size. We can also call those directly from rstan with the r hat function, or the ESS for effective sample size bulk or tail. So think about it for a minute here. What is going on here? Are these values okay? What might have caused this? Is this consistent with convergence? What helped you come to that conclusion? What might have caused this scenario? And can the sampling likely be improved without adjusting the model? So what's going on here is a case where we just have a fair bit of autocorrelation in the sampler. So they're oscillating around sort of a consistent value, but there's a lot of autocorrelation. I know that because I generated them like this. The R hats are a little bit big. The effective sample sizes are quite small. We've got 500 samples per chain, and the overall number of effective samples is only 52 because there's a high degree of correlation. Similarly, the effective sample size in the tails is small. But what we need here, if there was no way to tweak our model in some way, if we just ran this a lot longer, these values should come down, because I've actually created these from just an autoregressive time series. So that's an example where we've got autocorrelation in our chains. It's reducing our effective sample size, but there's nothing inherently wrong with it. We would just need to sample for longer to increase our effective sample size. What's the difference in importance of the bulk versus tail? I assume it would matter more whether you are worried about the tail probabilities compared to just the central tendency. So the central tendency, like if you want to calculate a mean from your posterior, you'd really want to worry about your bulk effective sample size. If you were worried about probabilities in the tails, you might be more worried about the tail effective sample size, but in reality, we're usually worried about both. So we want both to be reasonable values. This tail effective sample size is a newer innovation with that 2021 paper. Before, it was all just together in one effective sample size. And if you wanted to have better, performance in the tails, you just have to really ramp up that effective sample size overall. So let's run this second set of MCMC chains. So here they are sort of making a fuzzy caterpillar, but they are drifting over time. You can see that in our plot. Our R hats, because they're being folded on themselves, the right part is, when it overlaps the left part, is not going to align. And so all of our folded and split values are not great. We especially see it in the bulk and the R hat and in our visuals. So what might have caused this? I think a scenario where you might get this is if you started with values that were not overly dispersed in parameter space. Your initial values are pretty close, or maybe the same value, which is something sometimes people do, but you probably shouldn't do. And then you didn't have a long enough warm-up. Then your sampler has not yet diverged from the starting location into the posterior distribution. So we're still drifting over time, which is not a good thing. So we might need a longer warm-up. We need to make sure we start from dispersed starting points. Let's look at this one here. Visually with the trace plots, it's not maybe super obvious if this is good or bad, but I do see that this chain number 1, I assume, is ending up in slightly sort of higher and lower values. So it's a little bit suspect. There's other MCMC plotting built within Bayes plot. MCMC dense overlay does a density overlay style plot. So each one of these is a density plot for the samples from that chain. And here it becomes more obvious that, yes, chain 1 has a wider variance than the other chains. And if you see that in our hat not being great, effective sample size bulk is fine probably because the means between them is fairly similar. Effective sample size of the tails here starts to get lower because in the tails they're deviating from each other. So it's here's an example of what it means to look at the bulk versus the tail effective sample size, what they can diagnose. Probably a bit of an odd one. I'm not sure I would commonly see this, but given that the 4 chains have their own tuning, you could end up in this scenario if one of them ends up tuned quite differently than another and is able to explore corners of the posterior that the other chains are not. Regardless, if you were to end up in this type of situation, this is suspect, not great. And you might need to potentially think about having more constraining priors. Maybe you need to simplify your model. Maybe a longer warm-up, and they would end up with all similar good warm-up settings in their tuning. It's possible also you would need to play with that adapt delta to play with that acceptance rate. Maybe if they had a higher acceptance rate, a higher adapt delta value, then they would all be better at exploring further into the tails of the distribution. So here's another one, MCMC 4. That kind of looks okay to me there. That looks okay to me there. They're all overlapping generally. Our R hat is really small. It's less than 1.01. It's approaching 1.00. Our effective sample size bulk is high, and as is our tail. So this is an example of nice MCMC samples. I see nothing wrong with these. All these ways of looking at it, they look fine to me. So I would accept those as consistent with convergence. If we look at the 5th example here, not super obvious if something is wrong just by plotting the trace plot, but our R hat is not good. Our effective sample size is terrible. Our tail effective sample size is not great, but it's really only obvious why when we look at this density overlay. So in this case, I have created them with different means. And that's why we especially see it in the bulk effective sample size and our R hat. So our 4 chains, in this case, they probably started from random dispersed starting points, as they should and as they default in STAN, but they haven't converged to the same distribution. They're basically sampling from different parts of the posterior, which is a problem. We might need to play with our adapt delta setting, have a longer warm-up, but honestly, this would be fairly worrying and may require some thinking about the model itself. So here's an example of, looks a bit different from the previous one. So if we look at our trace plot, you can see they started in a dispersed starting point, and then they're bouncing around, somewhat autocorrelated, but looking fairly random to the right. Our R hat is a little bit high. Vector sample size is not great for the tail or the bulk. When you think about what has happened here, I would think what's happened here likely is that either the warm-up was far too short or you forgot to discard the warm-up samples and you're seeing the dispersed starting points. And then secondly, you have some autocorrelation in the chains, which as we talked about isn't a problem in itself, but it is going to reduce the effective sample size and require more samples or differently tuned sampling algorithm. As we saw in the Metropolis-Hastings one, if you had a jump distance that was too big, you'd end up with a lot of rejected samples. And so you'd end up with a high amount of autocorrelation. The same thing could happen here. So all about prior distributions. So what is a prior? Well, a prior is an encoding of all information that we bring to the analysis before, i.e. prior to our data analysis. There are several roles of the prior. One is to encode previous science or expert knowledge. 2 is constraint, so stabilizing our estimation. And they can also be seen as a nuisance. Sometimes they're used as a necessity, but are largely ignored. So where can we get expert knowledge priors from? Well, from previous studies, especially meta-analyses, but they can also come from our understanding as experts in a domain if we can convince others that our assumptions are reasonable. And that's really all we have to do. So something you may see in literature is something called proper priors. I just want to make sure you understand what that means. So a proper prior is just a probability distribution that integrates to 1 that is used as a prior. So a uniform that goes from negative infinity to positive infinity is an example of a prior that is not proper because it does not integrate to 1. And the nice thing about proper priors is that we can generate or simulate meaningful data from the models with proper priors in order to look at the implications of our priors in our model. Another term that you may see frequently is something called conjugate priors. So this is a prior that combines with a specific likelihood to make a posterior from the same family. This is most useful for analytical Bayesian calculations. It's also used in some MCMC samplers where they will detect if there is a conjugate prior, and then they can make more efficient calculations. But we generally don't need to worry about this with MCMC, especially within STAN. This doesn't actually have any effect. But an example would be something like a Poisson likelihood with a gamma prior results in a gamma posterior shape. So informative priors, don't see a lot of these, but they're fantastic. So we have an example of something like, a normal distribution with a mean of 4.9 and a standard deviation of 0.2 based on a paper by Smith et al. In 2004. That might be an informative prior. Weakly informative priors, and we'll talk more about this when we talk about Bayesian workflow and some exercises with priors. These are great. They're heavily pushed by the sort of STAN community, by Gelman et al. So as an example, for some scaled slope parameters, so we've scaled our data so that it has some reasonable standard deviation, like a standard deviation of 1. Then we might have a prior that's like normal with a mean of 0 and a standard deviation of 1 or 2, compared to something like a normal distribution with a mean of 0 and a standard deviation of 1,000. So the first one is constraining it to sort of reasonable effect sizes that we might expect in a system. The second one is allowing for some really crazy slope parameters. And then this is an example as well of a non-weakly informative prior, because now we've got a mean that is not 0 and a standard deviation that's quite tight. Conservative priors sometimes you see talked about, and this kind of gives away when I first made these slides. Conservative prior is a prior on a scaled slope coefficient that is reasonably tight to be conservative about the possible values of that parameter. So it might constrain them quite a bit. So for example, a normal 0,1 prior versus a normal 0,100 prior. Uninformative priors, something you will hear. And there's really no such thing, so don't call things uninformative priors. Priors just have more or less information in them, but even a uniform prior has information in it. And it can depend on the transformation of the parameter when it enters the model. Priors that let the data speak. So sometimes people talk about priors in that way when they have heavy tails. So here in the bottom right, you see a normal distribution in the dashed line, and then a Cauchy distribution, which is a very heavy tail distribution in the solid lines with shading. And the Cauchy distribution with a scale parameter of 2 has more density in the tails, and it's a bit tighter around the central tendency. So what this does is it says, I think some parameter is in this central area, but I'm still allowing probability of the parameter being really, really big or really, really small. Whereas the normal 0,2 would basically squash that posterior if it got into those values, because the probability is effectively 0 once you get more than a 3 or 4 standard deviations from the mean. So what are some example priors that could be considered weakly informative for different types of priors? Priors on slope parameters. Common choices would be a normal, a student t, Then student T, it's often written with the first parameter being the degrees of freedom parameter. As that degrees of freedom parameter gets smaller, the tails get heavier. If that student T degrees of freedom is 1, that is the same thing as the Cauchy distribution. So a value of 3, for example, has moderately heavy tails, but not as heavy tails as the Cauchy. And again, choosing some reasonable scale parameter like 1 or 2, assuming you've scaled your data such that you know that that's like a reasonable scale that the slope could be. Keeping in mind that Stan uses mean and standard deviation whenever it talks about normal distributions or other distributions. And that is because it's reflecting the way that it's coded, say, in R, like with D norm or R norm. But most of the statistics usually writes out normal distribution as a mean variance. Something to be aware of. When you're writing up results with Stan, it's often useful to be clear about whether you are writing mean standard deviation or mean variance. Priors on intercepts. Commonly, you would also use some normal distribution or Cauchy or student T, but you might have a much wider scale because the scale of the intercept is going to depend on the data itself. So it needs to be something that's not overly constraining that intercept. So usually larger than the slope coefficient. Priors on scale parameters. So these are things like standard deviations. So common ones would be half normal. So that's a normal distribution sliced in half, so it's only positive. And then a reasonable scale might be something like 1, 2, or 3. Again, it depends on the scale of the data and the problem. People often use a half student T. That's probably the most common that I see now, or maybe a half Cauchy used to be used more frequently. And that again just puts a little more density in the tails, so it lets it get bigger if it wants to. And if there's not much information in the data, these priors are going to pull that standard deviation towards 0. You may see two common ones being the uniform or inverse gamma. At least within the Stan community and sort of in Bayesian data analysis that Gelman and family push, they advise not using these priors because they're actually quite informative. The inverse gamma one, for example, doesn't put any weight right at 0 and puts a lot of weight at exactly sort of the mode of that distribution, depending on how you parameterize it. And the uniform distribution can put a lot of weight at high values. It makes a big difference whether or not you put that uniform on the log of standard deviation or the standard deviation because it gets stretched. So the other reason why it's not great for Stan, and we talked about the Hamiltonian dynamics, if you imagine throwing a ball over the trampoline, those equations work best when you have nice, smooth surfaces. And so the no-U-turn sampler is going to behave best when you have smooth edges to the posterior. The posterior is influenced by the prior. And so Stan is going to have the best sampling characteristics if you have priors with smooth edges, so things like a half normal instead of a uniform. Now, if the uniform had a high enough upper bound, you might never hit it, but then your prior is not really helping you as a weakly informative prior either. Priors on parameters bounded between 0 and 1. So examples might be the beta distribution, some examples there shown on the left, or the binomial distribution can be used. Priors on parameters bounded -1 to 1. Sometimes people do use the uniform there. If the parameter really doesn't make any sense above 1 or below -1, that can make sense. Or say a truncated normal distribution, truncated at those bounds. For correlation matrices is another example where something can go between -1 and 1. A common default prior is something called the LKJ prior. This is the default within the BRMS package that we will look at later. And the LKJ prior has a parameter that here, eta, which defines the shape top to bottom, and then left to right, I'm just showing this for different 2x2, 3x3, 4x4, and so on correlation matrices. And this sort of takes into account the fact that as you have higher and higher dimensions to your correlation matrices, there's an implied sort of minimum correlation that you're going to have between those values. So if you want to absorb sort of good thinking about priors and the choice of priors, this wiki on the Stan GitHub repository is great. It's quite casual, but has lots of gems in it, including this one that Aki prefers a student T, something about the shape of some curve he put on the blackboard, and I can't remember. I think that's Andrew Gelman writing. So if we go here, there's lots of information here. Principles about setting priors, how to think about how informative a prior is, what people like as generic priors for anything, and so on. So worth having a look, especially if you're trying to put a prior on something that you haven't put a prior on before, and you want to get some good ideas for how they should, what would be a good starting point. But in general, we will do some examples looking at simulating from your priors to see their implications. We'll do some examples where we look at how they constrain estimation and constrain the posterior to look at the sensitivity of the priors. But as long as you can explore the sensitivity of your priors and you can justify that you've chosen priors that are reasonable to a reviewer or reader, you're good. And in practice, that is a lot simpler than you might think or worry about. Let's just finish off today with this priors explorer.r. So this is a Shiny app, avoiding manipulate. So if we open up Priors Explorer, this is a little tool that I've created just to look at a linear regression, and allows you to play with the priors to look at the effect on the fit. I'm going to load the rstand-arm package. You don't need to know about rstand-arm. I'm just using that to actually fit the model in the back end in this case. I'm going to load the Shiny package. I have a little function here. It's going to take a bunch of things like my random seed, my true intercept, my true slope, my true residual standard deviation, number of data points that I want to sample, and then some information on the prior. So I've got the prior mean on the slope and the SD, the prior intercept SD, and the prior on that standard deviation, a half normal prior, I think, on the standard deviation, and then the length of each MCMC chain. So if I run that, and then I run the next lines of code, this should pop open a Shiny app for you. And I encourage you to play with this. You can ask questions like, what happens if you have a tight prior on the slope coefficient that differs from the true value? How does this change when you have lots of data versus little data? How much data do I need before the data overwhelm the prior? What happens with a very diffuse prior on the slope coefficient and very few data points? Can having an informative prior on the slope coefficient help if you've collected very little data? So let's go back to this. So if we have a true slope value of 1, let's look at what we're looking at over here. So this is our intercept in all of these panels. The blue is the prior. The red is the known true value, and then the histogram are the samples from the posterior. And then on the final panel here in the bottom right, I've got the data as dots, X and Y. I've got the true relationship in red, and then I've got some number, 50 probably or something, of samples from the posterior drawn as lines through the data. So if we have, say, a true slope of 1.2, and we put a prior mean that differs quite a bit from that, and I'll make the standard deviation on that prior quite tight. So I'm making this prior here tight. And if I reduce the number of observations, you can see here that our posterior is really getting yanked around by the prior. So we end up with a fit that is still a bit negatively sloped, even though the true value is positive, because this prior is pulling the posterior to the left. If I were to weaken the standard deviation on that prior, then suddenly it becomes easy for the observations to overwhelm the prior. And even if I had something like this, if I then increase the number of data observations, at some point I have so much data that it's really able to overwhelm that prior that was far off from the real value. and my fits basically resemble the true line, probably with a very tiny amount of bias. What if I have a very diffuse prior? Put this back to 0. Not a lot of data points. So let's go like that. So now we get some pretty sort of, wild draws from the posterior. If we were to have our prior on the slope, however, having a tighter standard deviation, it's going to start constraining those slopes so they don't do as wild things when we have very little data. And as an example of an informative prior, so let's say the true slope is 1.2. I then put this as the slope is at 1. I have very few, even here, with just 2 observations, I end up with a posterior that closely reflects the actual slope because my prior is informative and is able to pull the posterior to the true value.